Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings. I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. In our show last week, I referenced the Fermi National Accelerator Laboratory, the largest and most powerful particle accelerator in the United States. Also known as Fermilab, the lab is located in Batavia, Illinois, close to Aurora, Illinois, and about 30 miles west of Chicago, Illinois. My first research experience was at Fermilab. I was an undergraduate majoring in physics at Southern University in Baton Rouge, Louisiana, an HBCU, historically Black university. I had the opportunity to participate in the Fermi National Accelerator Laboratory summer program for minority students. It's a great program. Science majors, engineering majors from various HBCUs were brought up to Fermilab for the summer. You were given a project. You worked side by side with a real physicist. And you got paid. It was a summer job. We were housed in dormitory rooms right on site. You had your own room. How awesome to be paid to learn. I learned about the area of high energy physics. And I also learned that high energy physics and astrophysics are very, very closely related. High energy physics, among other endeavors, seeks to determine the smallest constituent of matter. Remember, first molecules were thought to be the smallest, and then it was discovered that atoms make up molecules, and so atoms were thought to be the smallest constituent of matter. And then it was determined that atoms were made out of protons, neutrons, and electrons. And they were thought to be the smallest particles of matter. Well, because of particle accelerators like Fermilab, we now know that protons, neutrons, and electrons are made up of even smaller particles called quarks, Q-U-A-R-K-S. And there's various types of quarks. When I said that astrophysics and high energy physics are very closely related, think of a circle, a full circle where you start out with high energy physics that deals with the smallest constituents of matter. And you go around that circle, you come to nuclear physics, studies the nucleus of the atom. Atomic physics studies the atom. Solid state physics studies solid matter. And you keep going around that circle: thermodynamics, electrodynamics, electromagnetics. You get to space physics that studies planets, our solar system. And then you get to astrophysics that studies stars, galaxies, black holes, nebula. So going full circle, you go from the smallest to the largest, and they're right next to each other. So there's a lot of overlap. And to demonstrate how the two overlap, I would like to share with you the paper that I published from my first project at Fermilab. I talk about how physics is the window into our amazing world of nature, and mathematics is the tool to open that window. This will also demonstrate mathematics as the tool that it is, that physics uses to try to get a handle on all the amazing phenomena that occur around us in nature. Now, another reason why I would like to share my paper with you is because, remember that overlap between high energy physics and astrophysics? I believe that there is something I would like to point out, that even though my project was in high energy physics, I believe it has implications in astrophysics as well, as we will talk about a little bit later. So what I'm going to do, I'm going to start again with that beautiful picture of Fermilab and some other pictures, and then we'll get to the paper. Okie dokie. Here's a beautiful picture of Fermilab. These rings are about 5 miles in circumference. And I'm going to bring up a schematic, but with this picture up, let me just call out some of what I'm going to show you on the schematic. That's the main building. And then you have a generator, and then the linear accelerator, which is called the LINAC. Then you have the booster synchrotron. And then you have the injector and the main ring. So the protons at Fermilab, they get accelerated in stages. Okay, they start out in this generator. They go to the linear accelerator, and then to the booster, and then to the main injector and the Betatron, capable of producing protons with an energy of 1 trillion electron volts. Notice the water canals that go around the injector and the Betatron. Also notice the water that's at the booster. So water, natural element, was used to help cool this system down. Here's a schematic of the Fermilab accelerator, the stages that the protons are accelerated in. They start off on this end from a generator. They're inserted into the linear accelerator, the LINAC. They gain energy, and then they're inserted into the booster synchrotron, where they gain more energy. And then once they reach a certain energy level, they're inserted into the main injector, okay, gaining energy. And then they are inserted into the Betatron, and they go in opposite directions so that the protons can be collided with each other. In high energy physics, using particle accelerators to collide protons at very high energies. Think of having a piece of wood that you want to try to find out what it's made out of. One of the ways to do that would be to break the wood apart. That's what's going on with particle accelerators. They're used to accelerate protons to enormous speeds, close to the speed of light, with huge energies, and then they're collided with each other to break them apart. That's how quarks were discovered. And as powerful as the Fermilab Betatron is, cosmic ray protons reach us with energies thousands of times greater from somewhere out there in space. There's some mechanism out there that we haven't been able to decisively determine. Supernova remnants are a top candidate, but we still don't really know what is it that's creating these cosmic rays, these protons that reach Earth with such enormous speeds. Okay, so back to my research project. It involved the booster synchrotron. And as we go further, let me describe to you how the protons are guided around the booster synchrotron. In order to transport the protons around the booster synchrotron, as well as the Betatron itself, magnets are used. Charged particles react to a magnetic field, whether they be protons with a positive charge or electrons with a negative charge. So a magnetic field can be used to guide protons. And in order to keep the beam of protons collimated, quadrupole magnets are used. And here's a picture of the quadrupole magnets that are used in the Fermilab booster and also in the Betatron. Think of transporting a beam of light over a long distance. You use optical lenses, right? To focus, defocus, focus, defocus. Quadrupole magnets, that's the exact same thing they do. 2 north poles, 2 south poles. They act as a focusing device. And dipole magnets are used to turn the photons into a circle. Okay. My research project, my first research project ever at Fermilab, involved tracking the Betatron oscillations of protons around the booster synchrotron. Now, just as with a light beam and you're using lenses to transport it, you're going to have some focusing, defocusing, correct? Well, same thing with protons in an accelerator. As they travel around the booster, the quadrupole magnets, yes, they're keeping them collimated, but unless a proton is going exactly down the middle of the tunnel, exactly down the middle of the quadrupole magnet, if it's a little bit above the trajectory or a little bit below, a little bit to the left, a little bit to the right, it's going to experience some perturbations. So instead of going straight down the middle of that quadrupole, it's going to oscillate a little bit. It's going to go a little bit up, a little bit down, a little bit to the left, a little bit to the right, if it's not exactly in the middle. And a rectangular coordinate system, the z-axis is down the middle of the quadrupole magnet. The x-axis is in the radial direction, and the y-axis is in the axial direction. So if a proton enters that quadrupole, not right center, a little bit in the x direction, a little bit in the y direction, it's going to experience an oscillation, and that's called the Betatron motion. And that space in which these Betatron oscillations take place is called phase space. All that means is that the proton is experiencing oscillations in the x direction and the y direction if it's not right down the center of the quadrupole. And that's what my project was. It was to figure out how to track the Betatron oscillations of protons in a synchrotron. Okay, so now let's go on to my paper. And again, I want you to see the physics involved here. And again, there's implications in astrophysics that I will come to a little bit later. So let's go through my paper, and I'll pick out certain parts of it, and then we'll see the physics and the mathematics that was involved. Okie dokie. And then, of course, we brought in the computer at the end. All right. Here's the cover page for my project. The tracking of the Betatron oscillations of protons in a synchrotron. And in this case, it was the booster synchrotron at Fermilab. My summer project. Oh, I was so excited and thrilled to be doing real research with physicists, high energy physicists. Okay, so let's page through here. I hope you enjoy. All right. Here I give a description of what I just told you about, what Betatron oscillations are, Betatron motion in phase space. And this is the physical phenomena that particle accelerators have to deal with. That the protons, as they're traveling around the synchrotron, they vary a little bit, okay? Yes, they stay collimated, but they vary along the x-axis and along the y-axis, but they're trying to stick as close to that z-axis, right? They go straight down the middle of the quadrupole magnet. And remember, many, many, many turns of the synchrotron are done to obtain the energy before injecting these protons on into the tevatron. Okay, okie dokie. Tune in next week, same fat time, same fat channel.